Good. Okay, so now we want to switch to a different subject, namely to von Neumann algebras. And in the last 2 weeks or so of the class, I want to show you what freeness can tell us about von Neumann algebras. I mean, that was really the context where it was introduced by Vaculescu to attack some of the famous questions on von Neumann algebras. And in particular, after we had this connection of freeness with random matrices, we also have the connection between von Neumann algebras and random matrices, and this really has quite a big impact also on von Neumann algebras. Good, but today I want to start with reminding you about von Neumann algebras, the basic properties which are important for us, but then go right away into the concrete von Neumann algebras we are interested, which essentially is a von Neumann algebra version of the group algebra, which we had in the very beginning as the motivating example for freeness. Okay, so this is the chapter of von Neumann algebras. And the ones we are in particular interested are the so-called free group factors. And then of course we should see how their structure relates to freeness. And good, so let me start with the basic definition. Just recall what a von Neumann algebra is. Okay. So, what is a von Neumann algebra? Used by von Neumann, and in particular in a series of papers by Murray and von Neumann. They were investigated in the 1930s or 40s, so von Neumann algebra. You have von Neumann. So what is this? So I'm taking, I mean you can define them abstractly, but they are given by operators, non-operators in the Hilbert space, so I will always take the concrete definition. So it is star subalgebra of the bounded operators on the Hilbert space. So star subalgebra E of H. H is the Hilbert space. I mean, generally in our case, usually infinite dimension, and B is the bounded operators on the Hilbert space. And so we have a star subalgebra. Also, since we have a subalgebra, star subalgebra means it's close to the star. So if X is there, then X star is also there. So anyway, what you say so for space H. So this subalgebra, okay, it should be unital, and the one should really be the identity operator of P of H. So it should contain, which contains the one of P of H, which is just the identity operator. But then, of course, it's not just an algebra, but it has an analytic structure, so it is closed under some topology. And the topology which we have here is, let's say, the weak operator topology. I mean, there are two types of topologies on bounded operators. One is the norm topology. If I close things in this, then I will get a C-star algebra. And then there is a class of weaker topologies, which more or less are all equivalent. So there's the weak and the strong operator topology. So let me say here, I'm saying it is closed against the 1, and it is closed in the weak operator. Okay. So this means we also allow that we can take limits of elements, and they are sequences of elements or nets even, and they are still in my von Neumann algebra. Let me remind that the weak operator topology, so this is a locally convex topology. This means it is generated by a system of semi-norms, which are all, by definition of the topology, continuous. And the semi-norms are given by taking inner products in my Hilbert space. So it's a locally convex topology. Defined by semi-norms. norm topology, I only have one norm, the operator norm. But if I go for bigger topologies, I have a lot of semi-norms, and all of them come to topology, and the semi-norms are indexed by elements in my Hilbert space. So theta, xi, and eta are vectors in my Hilbert space, and for each pair of such vectors, I have this semi-norm indexed by xi and eta. So which, if I apply to vector to x is an element in my P of h, then this is the inner product of x applied to xi is theta. Okay, so xi and theta are elements in the Hilbert space, x and this, again element in the Hilbert space, and here the inner product in the Hilbert space. Okay, so I have all those norms, and they create the weak operator topology. So this means if I have a sequence, or in this context usually one even has to use net, so if I have a net of elements which converges to something, this means that all those guys have to converge. Good. Then crucial, a lot, of course, this is an analytic object, it has topological structure, it's closed in some topology, but in the theory of operator algebras, in particular the theory of Neumann algebras, a lot of things can be characterized in terms of algebraic description. And so, what one usually considers in the von Neumann algebra context is not only the von Neumann algebra, but also its commutative. So, what is this? This can be defined for any arbitrary subset of bound operators. This is just a set. Then we define the commutant of this. Then we define the commutant of this set A by, okay, those are all bound operators which commute with everybody. So they are usually denoted by A prime. So those are bound operators. So everything lives in P of h. A is a subset of P of h, but then we are looking for the elements in P of h which commute with this. So those are y's in P of h, such that this y commutes with every x in my set. Good. Okay, and then we can also take the commutant of the commutant, which is called the bicommutant. And those are the guys which commute with everything, which commutes with everything. So, commutant, of course, so this is a double prime. This just means I take the commutant, and with this I take the commutant again. So this means these are elements which commute with everything, which are here. Those are elements which commute with everything in A. So it is clear that the bicommutant contains in particular A. But what it doesn't usually is it increases it, and if A is already a nice algebra structure, then really what it does, it takes the weak closure. And that's the most basic theorem about von Neumann algebras, this is the bicommutant theorem, that actually you can also characterize them by the fact that they are equal to their bicommutant. So there's a very nice algebraic characterization. Analysis and topology and algebra go nicely together in this context. Good. Okay, and maybe a final definition, basic definition is, of course they are commutative for Neumann algebras. Those are the infinity spaces of some measure, but we are interested in the non-commutative ones, and in particular we want to take the most non-commutative ones, so we wouldn't like to have many commutation relations within. So in particular, there should not be any element, apart from multiples of the identity, which commutes with everything. An element in the von Neumann algebra which commutes with everything in the von Neumann algebra, that's the center of the von Neumann algebra, and we require that this should be just the multiples of 1. Of course, von Neumann algebra contains the identity, and the identity, of course, commutes with everything. But that should take it. Okay, so such a thing we call a factor. the work of von Neumann. Okay, so for Neumann algebra, so this is called a factor. If the center, and this is the intersection between M and its commutant, M intersected commutant, because this contains the elements which commute with everything from here, and now we also require those guys should be in M. So those are the elements in M which commute with everything. And this should just be the multiples of the identity. Okay, and so I mean, in particular, what one wants to understand are factors. Because in principle, every von Neumann algebra can be built out in a commutative way out of factors as an integral overhead. Good, okay, so that's the basic definitions. So now maybe I will call some basic facts about von Neumann algebras. I'm not moving anymore, but I just remind you of them. Okay, so maybe as I said before, the most basic fact is this bicommutant theorem that we can characterize this closure in this topology also by an algebraic condition, namely that the algebra is the same as its bicommutant. So this is the famous bicommutant theorem, which goes back to Neumann. So for this I take the subset of B of H, but this should already have some algebra structure. So this should be a unital star subalgebra of B of H. So this unital subalgebra, and then we can characterize whether this is a von Neumann algebra or not, which by definition means it should be closed in a big operator topology. We can characterize this by the algebraic condition that it's the same as its bicommutant. So then maybe this Neumann algebra if and only if it coincides with its bicommutant. Or the other way, I mean, if I have here a star subalgebra and I want to take it's generated from Neumann algebra, by definition I should take the weak closure of this. But another way I could do is I just take the bicommutant, because this will then give me the same. So instead of looking on sequences in my A which converge in this topology to something, I can also look for elements which commute with everything which commutes with elements in A. So that's purely algebraic. Good. Okay, then I mean this weak closure in this topology, this corresponds in the commutative context more or less to pointwise convergence. And taking elements in this closure corresponds somehow to taking measurable functions. In the C-star algebra context, the norm convergence is like the uniform convergence for functions, and what you get in the C-star algebra context are like continuous functions. But here it's more like measurable functions. So this means, I mean, there are usually von Neumann algebras are very big because they contain these elements, also in the sense they're measurable functions. So in particular, they are closed under the measurable function matrix. So Neumann algebra measurable functional calculus. And this is something which we have in B of H. So I mean, we can take measurable functions of self-adjoint or even normal operators but let's say take a several joint, a several joint operator in my Neumann algebra, and I take a measurable function on, say, on the spectrum of this guy. The spectrum of this guy is a subset of R, and then I take function of this measurable function. This is measurable function. So I want to say that f of x, which is defined via measurable functional calculus for bounded operators of Hilbert space, that this guy is also in the von Neumann algebra. Of course, elements in the von Neumann algebras are bounded operators, so this means I should better not take unbounded functions, because I mean an unbounded function with a bounded operator is also an unbounded operator. Okay, so I should also take here only bounded functions. So I take a measurable bounded function, and then the statement is, then first of all, f of x is defined via general measurable functional calculus, and a priori, this is an element in B of h. It's a bounded operator. Okay, but here the point is that actually for Neumann algebras are closed under taking this, so here I have that f of x is also here. So if I have a Neumann algebra, then it contains of all the measurable functions of its elements. So this means, I have a lot of possibilities for dealing with elements in my von Neumann algebra. C-star algebra is only closed under continuous functional calculus. Good. Okay, and if I'm allowed to take measurable functions, then in particular I can take characteristic functions of intervals, and this tells me, and such a function is then a projection. And those are exactly the projections which show up in the spectral theorem for the spectral resolution of the von operator. And all those spectral resolutions, they are also in my von Neumann algebra. So I'm concentrating this in particular. Let's say, then I have a several joint operator. I mean, all these can also be done from normal operators, but let's take the several joint, and I take as my measurable bounded function the characteristic function, which depends on lambda, which is just the interval from minus infinity. The characteristic function of this interval from minus infinity to lambda. This is the characteristic function, which is 1 up to lambda, and then it is 0. This is a measurable and bounded function, so I can apply this to my operator x. And then this tells me that this guy is in my von Neumann algebra. And of course, those guys, I mean, first of all, the characteristic function is a projection, which means this function applied to x is also a projection in my von Neumann algebra. So this gives me a projection for each lambda. And those are the guys which show up in the spectral theory. And this. Then we have spectral theorem, the realization of all operators in the Hilbert space, spectral operators. We have a spectral theorem that I can write x as the integral over the spectrum lambda dx lambda. Oh, okay, good. I mean, this is not so important. The main point is that all those spectral projections are in my von Neumann algebra. And in particular, this means the von Neumann algebra always has many projections. On the C-star algebra level, there are C-star algebras which have no non-trivial projection. 0 and 1, of course, are always projections, but otherwise there might be nothing. Because with continuous functions, I might not be able to get projection. With measurable functions, of course, it's very easy. Characteristic functions are always projections. So this here tells me that all spectral projections x lambda of x are in my von Neumann algebra. In particular, von Neumann algebra contains many projections. Good. Okay. So this means that for Neumann algebra is usually a quite big thing. So I mean, if we start, let's say we start with just with an algebra or star algebra, this might be a thing which we can control. If it is given by generators, then I mean those are finite sums, finite linear combinations of products of my generators, let's say. But then if I go over to a closure, I mean this thing is getting very big. If I take the C-star algebra closure, I mean this is already quite big. But then if I take the von Neumann algebra closure, it's even bigger, and a priori it's not even clear that I mean it might not be everything. I mean, of course, B of H is a von Neumann algebra. But so if I take a subset and I take the von Neumann algebra closure, it's even not clear a priori whether I'm not just getting B of H, whether there are some non-trivial von Neumann algebras there. But it turns out. What this means, von Neumann algebras are usually very hard to deal with, to classify, and to compare whether two von Neumann algebras are isomorphic or not. Because I mean they are quite big and there are many possibilities for doing operations in them. And another very important operation is the polar decomposition. And all von Neumann algebra is also closed undertaking the polar decomposition. So von Neumann algebra and it's also closed under the polar decomposition. Good. Okay, so what is polar decomposition? I mean, this is somehow the decomposition of a general element, not necessarily normal, into easier things. So namely, if I have element in my Neumann algebra, which say is on P of H, then I mean we have a polar decomposition. I mean, bounded operators by Hilbert space, we can do a polar decomposition. So that's just a basic statement about bounded operators in Hilbert space. So let me first call this. So if X, let's say, is in P of H, then X has unique decomposition in P of H overall, and this is of the form. Yeah, so what is a polar decomposition? This means that I write my element X as a polar part and its absolute value. I'm writing it as u times the absolute value of X. Okay, and the absolute value of X, of course, where the absolute value of X, this is X star X, and the square root of this, which I can do, I mean, X star X is a positive element, so I can take the square root, this is again a positive operator in P of H, and then I multiply it with u. So what I'm doing here is like writing a complex number as its absolute value times its polar, its e to the I phi. Okay, this u in general, I mean for a complex number, this u is a unitary guy, but in general I have to allow partial isometries. Okay, so this u and u is a partial isometry. This means it maps a part of my Hilbert space isometrically to part of itself, and on the other part it is so. So anyhow, so this u is also a special element. I mean, X of course is very nice. This is a positive operator, in particular self adjoint. I mean, self adjoint operators and also unitary operators, those are elements which we can deal with very nicely. Okay. So I mean, here we are trying to decompose a general element, which is usually very hard to deal with, into components which have more properties, which we can deal with easy. So U is partial isometry. Okay, partial isometry. I mean, you can say what it does in the Hilbert space. I mean, first you have a unitary. A unitary is just maps. It's a bijective isometry. No? Okay, it maps isometric space to itself. Then we have an isometry which just maps the Hilbert space isometrically to itself, but it might have, it doesn't have to be surjective. And then a partial isometry is something which only is an isometry on a part of the Hilbert space. So on the other part it is zero. So it might also have a kernel. Also it maps part of the Hilbert space isometrically to itself, and on orthogonal complement it is zero. And we can, as usual, we can also characterize this in an algebraic way. So this that acts isometrically on the Hilbert space can also be written in an algebraic way, that U is equal to U star U. So for unitary we have that U times U star is equal to 1, is equal to U star. For isometry we only have U star is equal to 1, and for partial isometry we have something like this. Okay, that's the general thing which can show up here. And we're claiming we can write every element in such a form, and actually this is also unique if we require something about U. Also in general, just writing it in this form as a partial isometry is not unique, but if you require that the kernel of U is the same as the kernel of X, then it is unique. Because I mean, if X has a kernel, then U could act on this kernel in an arbitrary way. Okay. You should also fix this. Outside the kernel, it could act in an arbitrary way. So we ask that the kernel of U is equal to the kernel of X. And then this is uniquely determined. So for a complex number, I mean, this uniqueness is, I mean, for each complex number, this polar decomposition as the absolute value times the phase is unique up to the point 0. I mean, 0 of course has an absolute value 0, but we could write it as anything times 0. But if we want to fix this anything, then this anything should have this condition, which means this anything also has to be 0. So we should write 0 as 0 times 0. As 5 times 0. Not as 1 times 0. Good. Okay, so that's the general polar decomposition. And now the point in the von Neumann algebra is that in the von Neumann algebra, actually both parts are also in my von Neumann algebra. Okay, so one part is the square root, and this is something which already in the C-star algebra. Right? I mean, there we take a continuous function here, so this means this is already in the C-star algebra. Okay, but the other part you see is not really given directly as a function of x. So you cannot say this from this definition it is not clear what kind of function u is of x. And it's not a continuous function in some sense. So this means in general when the polar decomposition u is not in the C-star algebra, but it is always in the von Neumann algebra. So that's the main statement here. Both parts in this decomposition, so the absolute value of x and also the u is in f. Part which is not so clear as to u. And actually you can check this by using the bicombinatorial condition of the von Neumann algebra. So we're not, of course you could say I should try to write u as a limit of functions of x. But this is maybe not so clear. But it's better to see that actually u commutes with everything which commutes with x. Good. Okay. And that's the main facts about what operations we can do in von Neumann algebras and what living in von Neumann algebra. And maybe here I want to finally just to stress again that the beautiful aspect of this theory is really this interplay between topological and algebra. It goes together, and so I mean many things you can formulate in one way or the other, and usually you're switching between the 2 points of view. So Neumann algebras, logical and algebraic properties determine each other. The basic statement of this, of course, is the biquotient theorem. And this also means that if I'm looking, usually if I have a Neumann algebra, I want to classify them, but of course I only want to classify them up to isomorphism. No? Of course, I might have different concrete realizations of the same von Neumann algebra, so I have to say what do I mean that two von Neumann algebras are isomorphic, and actually the relevant notion of isomorphism is purely algebraic, because this algebraic condition implies all the topological conditions. So hence, the relevant notion of isomorphism is purely algebraic. So it means if I have two von Neumann algebras, that's M, which is realized on bond as bond operators on the Hilbert space H, and another von Neumann algebra N, which is realized as bond operators on some other Hilbert space K, then you say they are isomorphic. Now, definition of isomorphism between von Neumann algebras. Yes, if I have a star homomorphism involved with them. I mean, if they are isomorphic, there should be a mapping which preserves all properties, but it's enough to preserve all algebraic properties. So, isomorphic, if there exists a star isomorphism, goes from M to N. So this should be of course, a bijective map, which is linear, which preserves the multiplication. So phi of A times B is phi of A times phi of B, and it should also preserve the star. Phi of A star is phi of A, and then the star. Good. Okay, but of course, because those are analytic objects, you would expect that maybe we should also require that this is a continuous mapping in some way, so that it also preserves the topological properties. But actually, in this context, this follows. So, any star isomorphism is automatically continuous in the right topology. Okay, so this means if you want to check for Neumann algebras whether they are isomorphic or not, it's enough to find an algebraic isomorphism between them. Which, of course, in general is not easy, but at least we don't have to bother with the analytic properties, but they are coming essentially for free. Good, so that's the basic properties which I want to recall. So are there any questions on this? Because then we should go to our main example, which we really want to understand. This is essentially the von Neumann algebra version of the Kuh algebra, which we had at the very beginning as the motivation for our freeness. So for Neumann algebras are quite old. They are, 80 years or something like this. They were even introduced before C algebras. But they are quite, there are many still, a lot of open questions, because it's in general very hard to deal with that. In a sense, it has a kind of doing measure theory in a non-commutative setting. Good, but so let's look at an example, which is our main example of a von Neumann algebra, actually a factor, and it's an example which you want to understand better, or which Voiculescu wanted to understand better, and still you want to understand it better. So, basic example is the von Neumann algebra version. Von Neumann algebra version of the group algebra. Which we considered as the first example which we had, and in this context I also motivated the notion of freeness. Okay, but so let us first see how we get the von Neumann algebra formula. So what was the group algebra? So assume I have a group, let's say a discrete group. So this means I have the trivial topology on it, no? So I'm just summing over group elements, there are no integrals or whatever. So for discrete group G, we said the group algebra. This is just, those are just linear combinations of group elements. So the group algebra is denoted by CG. This is the sum over group elements. I'm summing over group elements. Okay, they have some coefficients, complex numbers, so I take linear combinations of them. So when I alpha G and C, but of course we also required in the algebraic context that this sum should be finite. So only finitely many of these coefficients are allowed to be different from zero. Because otherwise we would have an infinite sum, and in such an algebraic setting we don't know what this means, and there's no notion of convergence. Okay, so the group algebra is a purely algebraic object, so even if our group is an infinite group, of course if G is a finite group, okay, then I just take all linear combinations. But we will be interested mainly in infinite groups. So in principle, I could here sum over infinitely many G's, but I say only a finite number of terms should be taken. So we have the condition that only finitely many alpha G are different from zero. Good. Okay, now we want to go over to extend this to a bigger thing, essentially by allowing also infinite sums here. But of course, if we have to make sense out of infinite sums, we must say when do they converge to something. And of course, we can do this if we can embed this somehow in bounded operators in the Hilbert space, because then we have our topologies, and then we can say we take the closure, let's say the von Neumann algebra closure of this. Okay, and to achieve this, we should represent this somehow on Hilbert space as bounded operators. And I mean, the canonical thing you can do is a group or an algebra to get a representation is to let it act on itself by multiplication. Okay, so that's what we're doing here. So we let now this C of G, this object, this algebra act on itself by multiplication, and because things are generally non-commutative, the proof is non-commutative, so let's say we take the left multiplication, so multiplication from the left, act on itself by, okay, and I mean this, if you do this for a finite group, this is the usual, the regular representation which you do in group theory, and then you decompose this into a reducible component, representation, and so on. Okay, but we want to do this here in infinite dimension setting. What we get here is essentially what we're dealing with is the left regular representation of our group. So we let the group act on itself, but we have now to take completion. No? So we need a Hilbert space. And the group has now two tasks. I mean, on one side I consider it as elements in my Hilbert space, and on the other side I consider it as operators which act on this Hilbert space. No? And they are acting by multiplication. So first of all I need to make this guy here. I make a Hilbert space out of it, and this is I'm just doing by taking the L2 space. Also I'm taking infinite sums which are just which converge into L2 sums. So this is the canonical Hilbert space which we have in this set. So for infinite groups, I mean, for finite groups, the whole theory is trivial, essentially. I mean, there's no completion, so it's really only interesting for us if we have infinite groups, but then we have to go over to some completion. So we have to complete C of G, Hilbert space. This is just a 2 space, which means we take now again sums of group elements, linear combination of them with coefficients alpha g, but now we allow infinite sums, but they should converge in the sense that those guys in L2 now converge, the coefficients. So essentially we are saying the elements of the group form orthonormal basis of our Hilbert space. So we say that the sum over alpha g, those are complex numbers, over g is less than infinity. Okay, then this is a canonical Hilbert space. Of course, this is the usual product. Determined by, essentially by the fact that the g's are an orthonormal basis. Also, if I take the product between g and h, also g is just the element which has one coefficient 1 at the position g and 0 elsewhere, and h the same. So they are orthonormal, g and h, and h out of my group. And then for linear combinations of such guys, this goes just over by continuity and linearity. Okay, so now we have a Hilbert space. Those are given by sums of this, and now we can let these finite sums act on this. Also, we can now define a left regular representation of our group algebra. Now, left regular representation. Also, lambda. This is a representation of my group algebra, which still is given by finite sums, but I want to represent them as boundary operators in this Hilbert space, L2 of G, which is given by specific infinite sums. Okay, how is this action? So an element here is given by alpha G, where I'm summing over G, but only finitely many, different from 0, so this is just a finite sum. And of course, this goes here over. I mean, this representation should be linear. So this should, of course, be the sum over G, still a finite sum of the alpha G, and then here I have lambda of G. So this means I have to say what does lambda of G do. So I have to define the action of each element from the group on this L2 of G. And then, of course, this goes over to finite sums. Okay, and of course the action, I'm taking a group element and let it act on another group element. Of course the action is just by multiplication. Because that's the only thing I can do in multiply elements. lambda of G. So this acts now in element in the L2 space of G. But again, it's enough to say what happens if I'm acting, let's say, on element H, because this is the basis here. And of course, this is just given by G times H, which is again another basis element in my Hilbert space. So H is here also. Or maybe if we write it in general, so what this means by extensions of lambda of G, so the general element in my Hilbert space here is a sum of, let's say, alpha HH over the H's. So this is 2 of G. So this is an infinite sum, but the coefficients are square summable. And of course, this here tells me that this is then given by H of alpha H times GH. And this guy here again is square summable. Because I just have shifted the basis here. So the sum of all the squares here is the sum of the squares. So this is again, of course, the L2 of G. So I really have here an element. A mapping, linear mapping, from this space to this space, and actually this is a bounded operator, and even more for each element G, it's a unitary operator. Why this? Because the star, if you think a little bit, what is the star in this action? This is actually the same as multiplying this inverse. I think something like this we also do maybe somewhere in the assignment at the very beginning. But in the group algebra, the star corresponds to the inverse. All the properties of the group are somehow encoded in nice algebra or star algebra properties. Okay. And this in particular means that if I multiply lambda of G with lambda of G star, this is the same as lambda of G with lambda of G to minus 1. But lambda, of course, is a representation, which is also easy to check, so it's also compatible with the multiplication. So this is G times G to the minus 1, which is lambda of the neutral element in my group, and this is lambda. Oh, okay. And the same the other way around. So this is also the same as lambda G star lambda G. Okay, and this tells us that the operator which we get here in this space, the operator lambda of G, is a unitary operator. So each group element is represented as a unitary operator. And all lambda of G, and for G in my group, are unitary operators. So this means each G is represented as a unitary, in particular as a bounded operator, and then of course if I take a finite linear sum of them, of course this is then represented as a finite sum of bounded operators, which is again bounded. Of course, I mean, linear combinations of the G's are not unitary operators anymore. Because if I take linear combination of unitary operators, that's not a unitary operator. But each element in the group is a unitary operator. Okay. And so this is what we have achieved up to now. I have represented the group algebra, the finite sums, the finite linear combination of group elements as bounded operators on this L2 space. Yeah. But now we're in a situation that I have represented by group algebra, the finite sums over the group, on a Hilbert space as bounded operators, and on this Hilbert space I have a topology which allows me to go over to infinite sums. So now I can take the closure of this in the bounded operators with respect to any topology which I like. Okay, the canonical topology would be, one would be the norm topology, and this would, then I would take a C-star algebra. Then I would get a C-star algebra, and this would be a C-star algebra of the group. But what we want is to take the weak operator topology closure, and then we get a von Neumann algebra. Now, this is denoted by L of G. This is by definition. This is the group algebra represented in this way, and then taking the closure with respect to the big operator topology. And of course, this is still sitting in P of N2 of G. Okay. But if you like, you can also say, if you don't like to take closures with topology, you can also take the bicomitant of this. By the bicomitant theorem, we know this also is the same. So what we have here is that we take the group algebra represented in this way, taking out the closure, and taking the bicomitant. Much more algebraic object. And this is the same. Okay, so we get this. By the general theory, we know this is the Neumann algebra. That's the definition. And this is what is called the group for Neumann algebra. And that's the thing which we want to understand, in particular for specific groups. But this is already a construction which was in the early papers of Murray and Neumann, and this is really a very important construction for Neumann algebra. Good. Okay. So this L of G is Neumann algebra, and it is called group for Neumann algebra. And that's the Neumann algebras you want to look at. Good. And actually, this group for Neumann algebra comes with canonical state. Now, of course, at the end, we want to go over to non-commutative probability spaces. We always need a state. And already in the case of the group case, we had a very canonical state. And it's important to see that this state goes over to this Neumann algebra. So let us look on this state, which we denote by tau G in 1, 2. So that was defined on the group algebra. So it's then of form. So what was this tau? I mean, tau was defined on finite linear combinations of group elements. What was the definition? It was picking out the coefficients of the neutral element. So this was alpha of E. So we have here a sum over group elements, and we have coefficients for them, and this guy picks out the coefficient of the identity element of the group, of the neutral element. And this was really the state with respect to which we had this freeness. Okay, but so we record E is the neutral element. But so let me now maybe write it in the form. Of course, if I just say this, then it's not so clear whether this goes over to a closure. I mean, this is just purely algebraic. But now we have embedded this in our Hilbert space, as compound operators in Hilbert space, and the question is, can we extend this guy here to the von Neumann algebra, or even more? Okay, for this we have to write it in a way, in Hilbert space terms, that is clear that it can be extended, and if you think a little bit, I mean, you see that this here is really nothing else than acting with this element here, this is a finite sum, alpha G. So this is my, let's say my x. So if I say this is x. So if I'm acting with this on E, and take the inner product with E. E now considered, I mean E is a neutral element in the group, but now considered as an element in the L2 space of my Hilbert space. Yeah, why is this? Because I mean, what is the action of this on some vector? It's just multiplying. So I'm multiplying G with E. So what I get if I do this is I just get this vector considered as an element in the L2 space. But then I take the inner product with E, and I mean the group elements are orthogonal, so the only guy which survives from this side is the one if G is equal to E. And then I get this coefficient alpha E. Okay, so this is just of writing this here in a way which uses information from a Hilbert space. So this means that the state tau of x is nothing else than x e. The operator x applied to this special element and then taking the inner product of this special element. But this description is now something which makes sense, not even for our Neumann algebra, but makes even sense for all of P of h. And it's actually a state there. It's very easy to check. Of course, it's linear, but it's also positive. So in this form, we write it like this. Then we really see that we can extend our state from the algebraic frame to the going over this to the closure. Here even more. The state is defined in all of P of h, but actually on the Neumann algebra it has nicer properties. Namely, it is faithful and also trace. So it's really things which we usually also would like to have in our star probability spaces. Of course, we have now here a star probability space. We can take L of g together with tau. So we have a star algebra. I mean, the Neumann algebra is in particular a star algebra. It has more properties, but it's in particular a star algebra. And we have a state base. So we have a star probability space. For star probability space, the tau should be faithful, and that is a difference. So it is faithful, and also a trace. And those are things which you should check at least once in your life. Maybe not now, but I hope you have done it in some of the assignments for some of the operator theory or functional analysis lectures. Because this is really important. I mean, faithfulness, of course, is important to have a star probability space, but also the trace property is also very important. And in particular, those are properties which are only satisfied on L of g. I said, I mean, the tau itself, by this formula, can be defined everywhere on all of P of h. So it's a state on all of P of h. But on B of the Hilbert, on all bounded operators in the Hilbert space, it's not faithful and it's also not a trace. That is defined on all of E of G. And there, in general. Of course, I mean, if you have a finite group, then everything is finite dimensional, and then things are different. Okay, in the general infinite dimensional case, we're losing faithfulness, and we are also losing the trace property. Okay, why do we lose the trace property? Okay, this maybe it's not so clear, but actually you can show that on infinite dimensional Hilbert space, you don't have a nice trace which has nice continuity properties. So actually, there cannot be a trace. And this also shows you that this L of g cannot be all of this guy here. That was the question which I had. How do we know that L of g, if we take the closure of our group algebra in this topology, that we do not get everything, which of course would be very boring. We really want here interesting examples of Neumann algebras. P of h is a quite boring one. Okay, and here you see it cannot be all of it, because here you have a trace, and on all of P of h, there's no trace in infinite dimensions. Which means this cannot be the whole on operators. we have here is now for Neumann algebra corresponding to a group. And then I said in the beginning, usually we are interested in specific cases, which we call factors, where the center of the von Neumann algebra are just the ones, just the scalars. And it turns out that one can characterize this quite nicely in terms of the group. So if the group has a special property, then actually we even get here a factor. And this property is that the conjugacy classes should be infinite. And the typical examples which we consider have this property. So, I mean, in general, for general G, we don't need to get a factor here. I mean, if G is a commutative algebra, we get here commutative for our algebras. But if G is a non-commutative group, but non-commutative in a quite strong sense, namely ICC, and this means, by definition, this means infinite conjugacy classes. So this means that all the conjugacy classes, and the conjugacy class is if I take one element G and I multiply it by H and H minus 1 on both sides, and I'm running through all H's. So for all H in my group, so for fixed G, the conjugacy class of G is looking on all those guys, and the requirement is that all those classes should be infinite. Of course, if G is the identity, then the conjugacy class is just the identity. Okay, but all the other ones should be infinite. Which means, of course, in particular, that my group should be infinite. Okay, but it should be infinite, and of course, if the group commutes, then of course also all the conjugacy classes are trivial. So this means this is a kind of non-commutativity, but a quite strong one. So I'm asking that all those classes, the non-trivial case, which means G is not the identity element, they are infinite. Okay, and so if our group has this property, then it turns out that the group algebra is actually a factor. Then G is a factor. And then these von Neumann algebras are also called group factors. Good. Okay, so what are basic examples of such groups? I mean, those are the groups which we want to look at. I mean, we're taking those groups for constructing interesting von Neumann algebras or even factors. And then, of course, we want to understand which type of factors do we get, how many do we get, I mean, how much do they depend on the group, of course. So you have different groups, usually the group algebras will be different. But then if I take a closure, I mean, nobody guarantees that I'm not getting the same von Neumann algebra. That's one of the big questions in this context. And so, I mean, there are in particular two groups which give interesting examples, and the first one is the infinite permutation group. I mean, both examples were already considered by Roland and von Neumann. They introduced this construction. So what are basic examples of this? So of IIC groups, ICC groups. So the first is S infinity, which is the inductive limit of the finite permutation groups. So we can say this is the union of all SNs of n greater or equal to 1. So this is the infinite permutation group. This means you have infinitely many points which you want to permute, but you only permute a finite number of them. So this means that you're taking this infinite limit here. Of course, you could also commute as many as you want, but this would really be a very big group. This is too big. So this is infinite. Usually one considers as the infinite permutation group. So in a sense it combines all the finite permutation groups, and it's quite easy to show that this as infinity has this ICC property. Okay, it's not totally trivial, but it's not so hard to show. So this means if I take the corresponding for Neumann algebra, I get a factor. So this is L of S infinity, and this is a very famous basic factor, which usually is called R. So this is L of S infinity, and this is the so-called hyperfinite factor. Papers of 1936. And this is actually the simplest and nicest of the non-trivial for Neumann algebras. Of course, trivial for Neumann algebras are B of H and so, but if you really want an infinite dimensional example, which is not all of B of H, this is somehow the nicest and very well studied. And hyperfinite means, in some sense, you can approximate it by finite dimensional ones. In a sense, like you can approximate as infinity by the SNs. So if you can approximate this in a sense by matrix, by finite dimensional for Neumann algebras. Okay, and there has been a lot of work on this. In particular, one of the questions is, of course, there might be other groups which give you the same hyperfinite factors. That's one of the big questions. If I take in different groups, you get different the same for Neumann algebra. And for the hyperfinite one, it is known, but this is one of the big work of Kohn, that actually for all amenable groups, you get the same one. So there are actually many groups. There's a property of groups, amenability, and all amenable groups give you this factor. Okay, so big class of group, which for Neumann algebra level give you exactly one for Neumann algebra. Good. Okay, but that's. So this is well understood. And then maybe another example, which also was in the work of von Neumann, is to find another one. At the time of von Neumann, it was not clear whether there are really many of them. So what they did was they constructed essentially this R, this hyperfinite, and then they were also able to give another one of which they could show it's not the same as this one. Of course, they didn't have this result at all. Immediately group if you the same. This was Kohn, this was much later, 70s, 80s or so. Okay. So what they considered was the free group factor. So we're taking now for the group a very non-commutative group, namely the free group. So this means it's just a group which is generated by generators, and we don't assume any relation of them. So we take now for our group N, which is the free group on N generators. So this is hopefully it's clear what this is. Of course, this is a non-commutative free group. So this means I have N generators, G1 up to Gn, and then an element in the group is just any word in the G's, generators, and the inverse of them. Okay, such a word, good, I have of course the relation, the group relations. So I mean a generator and its inverse, they multiply to 1. So G1 times G1 to the minus 1 is the identity. So if this shows up in a word, I can shorten the word by this. But apart from those relations that, G to the minus 1 is the inverse of G, and also that the neutral element, if I multiply with something, gives this something. Apart from this, there are no relations between the generators. Okay, so that's the free group, and of course this is an infinite group. And I have this for each N. So I can have it for 2 generators, for 3 generators. Actually, N can be also infinity. For N equal to 1, of course, this is not so interesting because then it's a commutative group. Then I only have one generator, and I just multiply with itself and inverse. So I just take powers, positive and negative, and this actually is nothing else than set, the integers. So for N equal to 1, F1 are the integers, commutative group, but if N is bigger than 2 or bigger, then it is really a non-commutative group, and it's also not so hard to see that it also has this ICC property. So this Fn, this n greater or equal to 2. And one can also allow n equal to infinity. Okay, so this means we have again here a factor named L of n. Factor from Neumann algebra, which is a factor, and those guys, those or this guy, are called the free group factor. So this is a factor, the so-called free group factor. Good. Okay, that's now really the one which you want to understand. And then, as I said, they were already considered by Neumann, and they could show that this guy is not the same as the hyperfinite. So for all n, this L of Fn is not isomorphic to R. They introduced in some kind of invariant which can distinguish them. Okay. This is not totally trivial. Okay, so this means Neumann show that Fn is not isomorphic to the hyperfinite factor. This is true for all n. So all those Fn's are not a hyperfinite factor. Good. But that was more or less what they could show, and also after this not much more was known about the L of Fn's. And of course it is clear I have the Fn's for different n's, and this group they are not the same. The groups are not isomorphic. So this means I have a priori different groups, and the question is what happens with L of Fn? Are they the same or not for different n? And that's the big question which is open, since more or less it's the case of Murray for Neumann, and it's somehow an official question since the 60s or so, and that was what Golescu wanted to attain. And this question is still open. But we have learned quite a bit about the free factors. And that's of course what I want to show you in the next 2 weeks. What free probability allows us to, what kind of information we can get on this question. So let me formulate the question. Yeah, so we know it's not a hyperfinite one, so it's a different class or whatever of Neumann algebras, but we don't really know much about it. I mean, about the hyperfinite factor, a lot of work has been done. No? But the free group factors are still much more mysterious. So, but since then, not much more was known about, at least not until Golescu started to investigate that which they had the probability. So no, we know about it more. Okay, so in particular, let me formulate the basic question, because this is somehow the leading question of free probability theory. And it's maybe official question, since the paper of Kellison, which gives somehow a list of problems which he posed at some conference, and this was in 1967. So one of the problems there was this, and this is the following famous free group factor isomorphism. Problem. Also this asks, okay, this asks, whether the Fn for different n are isomorphic or not. So if this L of n isomorphic to L of Fn. Okay, so this is n, and this is m. And of course, I mean n and m should be different, and they should both be bigger than 2. Because for 1, this is a trivial object. So for n and m, both 2 are bigger, and n different from n. So one of them could also be infinity. Okay, so this famous question is still open. Okay. And when Voiculescu started free probability, he was looking on this question. So actually, before he had solved the same, he can ask the same kind of question on the C-star level. Instead of taking the von Neumann closure of your group algebras, you can take the C-star closure, and then, I mean, he could show, we work with spins now, so that they are not isomorphic. So if you go to the uniform closure, I mean, they are still different. But now if you go to a bigger closure, I mean, they might become the same, or not. We don't know. Good. Okay, so Voiculescu introduced free probability to attack such questions and similar questions. Voiculescu introduced and developed probability theory. This and similar questions. Good. Okay, so let me make a few final remarks. I mean, getting closer to free probability theory. Of course, I mean, it should be clear by now what freeness has to do with this. I mean, freeness was motivated by something like this. If our group is a free product of subgroups, but of course the free group is of course a free product of F1s. It decomposes of course as free product into subgroups. So this means the generators corresponding to different generators are free in this object with respect to the tau. We know this essentially on the group algebra level, but we should somehow extend this to the von Neumann situation. So let us think a little bit about what we have and what we really know already. Okay, so let us consider L of Fn and its generators. Consider Fn its generators. So the generators of Fn as a group, let me call them G1 up to Gn. And of course, I mean, they are now represented as operators on our Hilbert space, and we know they are represented as unitary operators. So maybe then I call them Ui. So Ui is the lambda of Gi. The GIs are the generators of my free group. So the I is running from 1 up to n, where G1 up to Gn are the generators of so group algebra is generated by linear combinations of those and their inverses, which means on a Hilbert space level, I mean, this is the group algebra generated by the UIs. Okay, and as we already saw before, the UIs are all unitaries. So from part 1 of this remark, all the UIs, so they are elements in our Neumann algebra, Okay, now of course what we are looking at are usually moments of objects, and of course we have this state tau. Oh, okay, so what are actually the moments of such a UI? So each of them is moments. So what are the moments? So we take tau. Oh, this is our state. Canonical state here. So I'm looking on UI, our k. So just a moment of the UI. Not mixed moments, but just looking on them. And so this is, what is it? So this is vi to the k, e over e in this rotation. And ui, of course, that's the generator. So if I'm acting here, I'm multiplying with the generator. So this here, of course, is nothing else than multiplying k times with the generator gi. If k is negative, then of course I will get the inverse of the generator. And so what I have here is the inner product between powers of the gi and the identity element. But of course I have a free group here, so no power of my generator is the identity. So all the powers of my generators are different group elements. There's no relation among them. So this means this here is 0 unless k is equal to 0. When I just have here the identity. So this is k 0. Okay. So this means I have here a unitary operator of which all powers, plus and minus, vanish under tau. And that's exactly what we call a high unitary element. So this means every generator of our L of Fn is a high unitary element. This means each UI unitary, of course, in, okay, now we should use our language, in the star probability space. So our star algebra is L of Fn, and the state there is tau. Of course, this is a star algebra. It's a von Neumann algebra, but for this statement I doesn't care about this. The only point is that tau has to be faithful on this. But that's something which I told you is true and which is not so hard to check. So in this star probability space, each of those guys is a high unitary. And of course, we also know the relation between them. They are free. Because that's exactly what we checked in the very beginning. And this was more or less how the definition of freeness was made. It was made exactly in the way that those guys are free. Freeness captures exactly this here. So, because we have here a free product situation. Furthermore, so Fn, the free group of n generators, can be written as a free product of subgroups G1 up to Gn, where each of them is just a subgroup generated by one of the generators, which of course is then just as a group isomorphic to set to the integers. So where Gi is the subgroup generated by Gi. And this means, of course, that each of the subgroups is just isomorphic to set. I mean, subgroups are commutative groups, so they are just powers of this one element, and they are isomorphic to set. So the free group, the Fn, is the free product of n copies of set. Okay, but then this situation, it was exactly in 1.3 where we checked that the fact that I have here free groups in this group translates in the language, in our non-commutative probability space language, into the fact that the operators are free with respect, or that the generated subalgebras are free with respect to tau. This. C of the GI are position 1, 2, 3, the very first chapter. They are freely independent in this sub-probability space N equipped with the state tau. Yeah, okay, so this means in particular that the generators, the UIs, U1 up to UN, are free High-unitaries in this guy. Each of them is a High-unitary and they are free, because the freeness just means the star subalgebras are free. Okay, so in this sense, L of Fn is generated by n free High-unitaries. Okay, the idea is whether we can get more out of this. Maybe one thing here is, of course, I mean, for those statements I have not really used that I have for Neumann algebra here. I mean, essentially those are statements about the group algebra, and that I'm looking into the von Neumann algebra is not really showing up. I mean, I'm saying, when I'm saying that the UIs are free here, this just means that I can control polynomials by definition. The definition of freeness means I'm looking on polynomials in my generators. But of course, when I say this guy is generated by the UIs, I mean it's generated as a von Neumann algebra, which means I should not only look on polynomials, but also look on general measurable functions. Okay. And I mean, of course, there is a discrepancy which we should close, that this notion of freeness essentially also goes over to this closure. So this means if I have operators which are free, it should not only be that polynomials in them are also free, but it should also be that measurable functions in them are free. Or if I have subalgebras which are free, then the generated von Neumann algebras should also be free. Because only then I really have the possibility to go over from generators and the fact that I have freeness there to some meaningful statements on the level of the von Neumann algebra. Good, okay, but that's something which is true, which we will see the next time. And actually, I mean, freeness really is something which goes over from algebras to von Neumann algebras. And this is really the important thing, so that we are able to lift more or less everything which we did before from the purely algebraic level to von Neumann level, where we take closures of things. Okay, so